All right, good afternoon, everyone, and thanks for coming on a few hours before Thanksgiving. Any questions? Yes?
For homework B, is it okay if you add an instance variable to the main class?
To homework B, let me look.
They specifically just to keep track of whether it's the last node or the last.
Okay. You want to put an instance variable into the node? No, that's considered really bad, right? Because you don't want to mess with the tree. Also, it would seem to be fragile because suppose that you have two concurrent threads print the same tree, then it wouldn't work, right? If they update it differently. So what are you trying to achieve?
I just wanted to add, say, the node is the last child, right? And I don't want to.
If it is the last child, so you want to find out what does it mean for, let me get some.
For example, if you're on Edward.
Okay, so if I am on Edward here, so let's see, what's characteristic about Edward? I see. If it is the last child, here is certainly how you can do it. You can pass in from the left, because Edward has no idea whether he's the last child. But as so often in life, his parents know. And so you could, on one level higher, you could, you have some recursive function, right? I'll call it print. And so what you're passing in is the child. You're passing in some prefix, at least if you're following my recommendation. And you can certainly pass in a Boolean is last, if that's helpful. Well, there's a print method that I have, and that instantly calls some helper. And the helper is entirely under your control. You can do anything you want with the helper. I've given you a suggestion that worked for me, but if you want to do it differently, you seem to have a different approach in your mind, that's perfectly fine. So you could make it so that your print method calls on each of the children that it calls print, for the child, and then whatever the prefix is, and then either false or true, depending on whether it's the last one or not. And that way, the child would know because it knows it from the parameter, and you don't have to store it in the node itself, and do weird things with the payload of the node. Would that work for you? Yeah. Yes.
Do we need a helper method or the helper method?
Well, I don't think you need one, but he seemed to have a different algorithm in mind, and that may be a good way of doing it. I haven't really, I have no opinion. I mean, I have a particular way that worked for me, and that's the way that I described, that you just need this one helper method. But you can set it up, there must be a million different ways of setting it up. Like here, the one that I have would probably be, it looks like it would be a static helper method, whereas the one that I have here looked like it was non-static. And, I wouldn't fret much over it one way or another. One of the two will work. So if you have a basically working scheme, don't mess with it just because you think it looks a little different than mine. So the one caveat is that obviously what I did not want people to do is to have a set of 4 nested loops. There was someone who said, oh, I can pass all the tests with 4 loops, meaning 1, 2, 3, 4 loops, not the for loop, not the for loop. And I said, well, that's clearly not intended. And so I tossed in an extra test case where one would need 20 loops, which hopefully that person didn't retrofit his or her program to now add 20 loops. So it should be a general solution with recursion. But otherwise, how it works, there's many ways of doing it. Other questions? Yes?
So
So a wise man once said, all work and no play make Jack a dull programmer. But is it true that there's no class next Wednesday?
There is a class next Wednesday. Why wouldn't there be?
It says December 2nd, no class.
Is that already next Wednesday?
Yeah, next week.
Oh, yes. Okay, so I need to ask for a sick day. I have a dental treatment on the day before, and the dentist said you will probably not be up to it. So there will be confidentially no class, but I haven't gotten the permission from the department yet. But I'm sure I will once I send them a photo of my bleeding mouth. So yeah, so there's no class on Wednesday, and that's fine. So basically, there was like a filler because it's always something that happens every semester. There was a filler for a final review, and I've just nixed that. So no class next Wednesday, and a class on Monday, and that'll be that. Other questions? All right, so let me go ahead with the lecture, and then if we have some extra time, I'll give some tantalizing hints for the final and what you might be doing with shell programming. So this is a pretty interesting tree algorithm that looks complex at first, but is surprisingly easy, and it makes use of a data structure that's otherwise somewhat underappreciated. So it's this Huffman coding thing, and here is this code that was from the book, and you can see how it works. Let's suppose that you want to encode the letter K in this code. Then you go to the left, that's a 0, then to the right, that's a 1, and to the left again, so it's encoded as 0, 1, 0. That's how the coding scheme works, just to see that everyone knows how to do it. We'll have a clicker question in a minute. But so the idea is that the leaves contain the symbols that we want to encode. The things that are not leaves, the interior nodes, they are just there to carry us along. So you can see here we're encoding the letters L, H, O, K, U, and so on. And you may ask, why this set of letters? Because if I had done it with all the 26 letters in the English alphabet, I would have had a hard time fitting it on a page in the book. So these are the letters from the Hawaiian alphabet. So the Hawaiians don't seem to need all these letters. And these are actually the correct frequencies. So the remarkable thing about it is that no code is a prefix of another. So for example, if you look at the code for H, which is 0001, then all of the things that are before that, the 0 by itself, or 00, or 000, are not code words. And that's important for decoding, of course, because otherwise you wouldn't know. Let's say for the sake of the argument that 00 meant X and 0001 meant H. That would be bad, because then when you see 000, you don't know whether to take this as an X or whether to keep on going. But because of this feature that no code is a prefix of another, this can never happen. And so you always know that you can stop at a particular time. And so the prefixless property is simply a consequence of the fact that the interior nodes don't have any letters marked on them. The interior nodes always say keep on going, and so that way when you follow 00, that's from here to here, then it doesn't yet encode anything. So that's what it is. It's this prefix free code, and the way that you want to make a code like that is, of course, so that it's as efficient as possible. So as you notice, some of the code words are short and some of them are long. So the A is 10, and the H is 0001. So it's twice as long, twice the number of bits. So obviously we want to design it so that more frequent words get shorter code words. It's just like in Morse code. Right? You remember Morse code from your Boy Scout days. You have dots and dashes. And so an E is a dot, a T is a dash, a dot and a dash is an A, and then a dash, dash, dot, and dash is an X, because that's a less common letter. Is it? Okay. My Boy Scout days have been long ago. So let's just try this to see that you can use this. So tell me real quickly which of these is the encoding of the one Hawaiian word that we all know. Where the heck's the L? Here. Oh, 0, 0. Yeah, how many people do you have? Or is everyone going to be voting from wherever they're stuck in traffic? All right, so each time you just, for the A, you find the A and then you find the path to it, 1, 0. For the L, I had a hard time finding it. It's all the way over here, 0, 0, 0, 0, and so on. So I think I can trust that the majority will find the answer. And so the majority says it's choice 2, with a non-trivial number of people saying it's 3. Let's find out why. Oh dear. So this one was an A, this one was an L. What the heck was the O? 0, 0, 1. So 0, 0, 0, 0, and then the H was this, and this one was the A. So I think this one was the right one. So is that reasonably clear? Easy? So that's this encoding scheme. And so the idea is that you want to encode with a minimum number of bits, and that of course depends on the frequency of each of the letters. Now this is a very practical scheme actually. Every time that you use a GIF file, for example, it uses this scheme to encode the colors, and we're going to see that in the in our example a little later. So it's not just something of theoretical interest. So anytime that it doesn't bother you that you have a variable length code and you want to give short code words to frequent symbols, this is the way to do it. So just to get another understanding of this, so there's a bunch of coding schemes that you have seen for letters that are quite different. You've seen the 7-bit ASCII code that one uses for all the American letters. You've seen UTF-8. You're somewhat familiar with Morse code. And so my question is, are any of these Huffman codes? And you might say, Huffman codes always have ones and zeros. Well, of course, the 7-bit ASCII code, has a sequence of 7 zeros and ones. UTF-8 and everything is a sequence of 1 to 4 bytes, and each byte in itself is 8 bits. In Morse code, well, you have short and long, so that could be 0 and 1. So my question is, which of these is not a Huffman code? Yes, so we're somewhat evenly divided here. So a lot of people seem to think that Morse code is not a Huffman code, even though it certainly has the desirable property that short symbols come before the longer ones, right? So the more frequent ones. So this is E and T. What's this? W. That frequent symbols have short encodings. But why is the Morse code not a Huffman code? So it looks like, right, this would be 0, this would be 1, this would be 0, 1, 1, 1. What's that? Well, they're not really grouped by threes, but you have something right with the 3 is I'm making it look like that it was a binary code. But it really isn't a binary code, yes?
It has prefixes of elements. Like the W has prefixes.
Yeah, but actually it's more subtle than that. If you look at, for example, 4 dots in a row, I don't even remember what that is. I think it's an H. Let's say it's an H. And now you look at 4 E's in a row. There's a subtle difference, yes?
You said that it have to be a bit interior nodes. If we can't have, so in the case of W, you wouldn't be able to tell if it was E, T, T, G.
Right. It's actually more than that because when and it would help if you've done this when you were kids, that to understand Morse code, it's not just the dots and dashes. It's the dot, dashes, and the pauses. The pauses are of crucial importance. So when you hear a short tone followed by a short pause, then it's an E. But when you hear 4 short tones in a row, then it's an H. And so if one didn't make pauses, if you just had this steady stream of long and short notes, no one would be able to apply the Morse code to it. So there's actually a third symbol, and that is the pause symbol that one doesn't normally write down explicitly. But a Morse code doesn't have just zeros and ones. It has, so to speak, zeros, ones, and twos, where zero would be might be a dot, 1 would be a dash, and a 2 would be the pause. And without the pause, you would not be able to make any use of Morse code. So it's not even a binary code, and therefore it can't be a Huffman code. So what about UTF-8? UTF-8 certainly looks like, if you remember, an E has a fairly short encoding with 1 byte, and some of the lesser used symbols, like the cat with heart-shaped eyes, uses 4 bytes. Was it 4 bytes? Yeah. And so it is a variable length code. And so one could perfectly well say, yes, it is a Huffman code. And it kind of is. And 7-bit ASCII is also a Huffman code as long as you're not bothered by the fact that we're not really taking the frequencies into account. So on the other hand, you could say, well, you know, we should be taking the frequency into account, and then you might want to argue for option 4. So this one, depending on whether you think the frequencies are important for ASCII and UTF-8, you could go either way. So there's no totally true answer for this one here. I just wanted to put this in perspective with codes that you know. So now what the challenge is, you have some symbols, and they don't have to be letters. They can be anything. We're going to be using colors. And they occur with some frequency. And now you want to encode a sequence of those symbols with the minimum number of bits. And so a very common application, like I said, is image processing. So your camera takes a photo, and then it wants to use the smallest number of bits to represent that photo. And what your camera actually does, as it saves the photo, is it figures out what is an optimal Huffman tree encoding for all the pixels. It really does that. And it's a different one for every image. So it goes through the image, counts frequencies, and then builds an optimal tree and uses that. And the decoder has the tree in the beginning of the image and reverses the process. So it's a very practical thing. So here I've taken an image done by one of my delightful children that has a bunch of white, a bunch of orange, a bunch of pink, they're girls, and small amounts of yellow, blue, and green. And I've given here some approximate frequencies. And so now we want to find an encoding that makes the code for white pretty short, because white is so prevalent. That makes the code for green, we don't care how long the code for green is, because it only occurs so rarely. And so we want to figure out, how do we assign code words to these frequencies? And so the algorithm somehow has to give us a binary tree, like the one that we're seeing here. It looks like if half of the colors are white, then if we give white a single bit, that would be pretty good. And with green, it could be long. We don't really care. And this algorithm, invented by this fellow Huffman, gives us an optimal tree for this purpose. Interestingly enough, Huffman was a graduate student when he invented this algorithm. So hopefully many of you will go on to be graduate students with names that we will later teach to your successors. And so here's what he invented. He said, we're going to add all of the nodes to a priority queue, so that the priority queue gives us what are the least important nodes. So ones with the smallest frequencies. And we're going to take the two with the smallest frequency and join them together, give them a parent. And that way, the ones with the smallest frequencies are going to end up far, far down in the depths of the tree. They're going to have long encoding sequences, and that's fine with us, because for small ones, we don't really care. And so we're going to make a parent for them. We're going to say the parent gets the sum of the two frequencies of the children, so that eventually the parent is going to get more important, and we don't just penalize them too much. And then we add the parent to the priority queue. So our priority queue is a queue of nodes, and each of the nodes could have children. So there's a picture here that I think makes this pretty clear. So we're starting out with a bunch of nodes, and each of them has the percentage in its data field. We put them in a priority queue. Now we're taking out the two smallest ones, the 2 and the 3. We're making them into a tree that now has a parent node. The parent node has the sum of these two. That's the 5% here. We're tossing that node back into the priority queue. So now the priority queue has 5 trees in it. So notice that before it had 6. Each time it has 1 less. So now we're doing it again. The least frequent ones are this 5 and this 5. And so they add up to 10% here. Then notice this one here goes over here, and this tree becomes the subtree over here. So we toss the bigger tree back in, and now we repeat it. And now it gets to be a little bit more interesting. So now we're removing these 2, and then when we add them back in, then that gives us a tree with 30% on the top. And let's see what children. One of the children is this 20% here, and the other one was the big one. So this one goes on one end, and the other one goes on the other end. It does not actually matter which end either one of them goes, so you can just, whichever one you find. All you're looking for is an encoding scheme. So at this point here, the cumulative weight of all of these has been such that it's gotten to be a little bit further back in the queue, but as it happens, it still gets combined with the next one. And so now we have these trees here with 50% each. You know, the 50% came from the 20 and 30%. And we still have 2 trees in the queue. So in the last and final step, we take them both out, and on the top we now have 100%. And now we're done. So at this point, the queue only has a single tree in there, and that is the encoding tree that we need. So in this encoding, white will be encoded as 0, and green will be encoded as 1, 0, 1, 1, 1. And so it's a simple algorithm. You know, it takes just a few lines of storytelling pseudocode to describe. And that's what it does. So here is the final result of the code. You know, white was short, green was long, and orange was somewhere in the middle. Now, by the way, when one says it's a code, it's not a code for encryption. You're all familiar with the kind of codes that one uses to encrypt secret data for whatever plots or romantic letters or whatever. That's not one of those. It's obviously anyone who has the tree can do the decryption, and also if you don't have the tree, if you know the frequencies, you could reconstruct it. So it's nothing secret. The whole purpose of the encryption is compression, is to make data shorter. You know, this is what, like I said, this is what goes on in GIF files, in zip files. This is the common strategy to crunch down a bunch of data into something that uses fewer bits. And so again, notice the prefix property here. So white is 0, and therefore none of the other code words can start with 0. Orange is 1, 1, and all of the others start with 1, 0. Pink is 1, 0, 0, and none of the others start with 1, 0, 0. So you can uniquely encode. So the implementation is pretty simple. We want a priority queue, and a priority queue needs things that are comparable. We've never really used the priority queue. There's one toy example in the book, but we've not really used it so far. But it is actually a pretty useful data structure. So a priority queue is this thing you toss in things. In this case, we're going to be putting in nodes. And whenever you say, give me the head of the queue, then it gives you the one with the highest priority. And for traditional reasons, because we always say priority 1 is the highest priority, it'll give us the one that is the smallest in the comparison order. So it needs the elements to be comparable so that it can find out what is the minimal one, and it gives it to us. We're not learning that in this class. You're going to be learning that in 146, how a priority queue is implemented. It too uses a tree structure, but a different tree structure. Right now we're just using the priority queue as a black box. It just does its thing. It does it efficiently. In terms of efficiency, it can well, I guess that's not too remarkable, but it can retrieve the shortest element in O of log n and insert an O of log n, but it does it more efficiently than the tree structures that we're going to be seeing next Monday. So just trust me, it's efficient, and it does its job. So in the implementation in the book, for whatever reason, where this frequency here is an int, it's a count and not a floating point number. I forgot why that was so. It just is. And then you see here a node is just like a regular tree node. It has a left and a right child. In its payload, we're remembering the character. One could have, if one wanted to encode colors, you could have put in objects, or we'll just say, G is green and O is orange. And we have to have a comparative function because that's what comparable tells us. So we also need the frequencies because the encoding is critically dependent on the frequencies. And so for each character, we need to have how often it occurs. So we'll have a map that says that an A occurs 1,000 times and a B occurs 347 times and a C 123 and so on. So for each character, we get to know how often does it occur. So then we make a node for each of them. So we have in the frequency table the key set, that's the characters that we wish to encode. If we have the English alphabet, it would be A to Z. For the Hawaiian alphabet, just that much smaller set of letters. And for each of those, we make a node. We set the character. We set the frequency by simply pulling it out of the frequencies map. And then we add it to the priority queue. The priority queue will internally keep them not quite sorted as it happens, but so that whenever we pull one out, we get the smallest one, the one with the highest priority. Now, in the loop, while there's more than one node in the queue, we remove the two smallest one. We now make a new node. We make the two that we have pulled out into its children. Like I say, it doesn't really matter in which order. We add the frequencies and say the sum of the two frequencies is the frequency of the new node. And then we add it back in. Eventually, this algorithm will come to a halt when there's no longer two that we can pull out. At this point, there still needs to be one because we just added one back in. And we take that out, and that is the root. So that's all. It's a very trivial implementation, really, that mimics almost exactly that pseudocode. Okay, just to see that everyone's paying attention, I omitted one line of code in here, namely in the compare to method, and I want you to fill it in for me. So there's two things that we need to decide. One of them is, do we want to compare the character values or the frequencies? And now in this case, when we want to pull out another node, we clearly want to pull out depending on the frequency, so that the more frequent ones get handled differently. The characters, we don't really care. And so that means that 1 and 2 should be kind of out of the running. Let's hope that that was pretty much the case, right? And so the only question is which order it goes. And so we want to have the lowest frequencies pulled out first. And so now we need to know what does the priority queue give us when we say give us an element in this call here. We're saying remove, right? We're not saying give us the lowest one, we just say remove. But as it happens, the priority queue is built like that, that gives us the lowest one first. So in this case, we simply need to arrange for it that lower ones give us negative values, and that is the one over here. Oops, no, I didn't mean to. Go away. Now what did I do? Okay. So I didn't mean to cross it out. This is the right answer, and that's what most of you got. All right, that's good. So that's the building of the tree. Now, how do we decode? So we've built the tree, and now we're ready to use it for decoding. And that one is really pretty simple. So when I have a string, then I start at the root. I'll just give you an example in the picture here instead of going through the code. So we had that string aloha, right? All in uppercase. And so when, no, that's wrong. I'm wrong. Decoding is the other way around. Decoding is if I have like 1 0 1 1 1 1 1 1 0 0 0. And so then you start at the 1. Go right. When you see a 0, you go left. Now you're at a leaf, so you say, hooray, I found 1. And now you reset yourself to go back to the root. And then you do 1, right, 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 and you find an A, and then you go back to the root, and so on. So that's what the code will say here. So n is the root. For each 0 or 1, we decide whether we go to the left or the right. And now when it's a leaf, is that right? Why does it only check whether the left one is null? Doesn't a leaf have to have both the left and the right to be null? Normally something is a leaf when both the children are null.
You messed up.
Yet again, yeah. Or did I? Would I be standing here this confidently if I had messed up again?
Because you load the group's node from left to right, so if the left is null, then the right must also be null.
I mean, you're right in that when the left is null, with a Huffman tree, not with any old tree, but with a Huffman tree, either both children are null or neither of them is. When we look at this tree, there's never a situation that only one child is null. Right over here, you have neither of them is null. Over here, both of them are null. And that's true everywhere. And that is true for a very simple reason. Namely, whenever we make a new node, we set both of its children to something non-null. So all the interior nodes have two children by construction. And therefore, in the check over here, we don't have to worry. We could say if n left equal null and n right equal null, but it's not necessary to check for. So that's a little subtlety. So anyway, when we find a leaf, we say, oh great, we take its character, we concatenate it with the result string, and we start back at the root. And that's the decoding algorithm. Now encoding is a little different. That's what when I just messed up and I say, okay, let's encode aloha. That seems harder because I first have to find the A and the L, and then I have to remember how I found them, right? And how the heck am I going to find the A? It could be anywhere. So it looks like encoding is pretty expensive. Right? If for each of the symbols, I have to migrate through the entire tree until I finally find it, then that means each encoding is an O of n operation. And that would be bad, but if you think about it, you only have to do it once and then you can remember it. If you remember in some table that the encoding of A is 0, 1, then the next time you see an A, you don't have to do that computation again, you can just look it up. So the time-saving idea here is that before you encode anything at all, you build up that table. So let's defer encoding for a bit and let's say, how can we build up this table? And so the way you would build it up is to say, well, what's our job? We need to fill in a table that has a, do we have a B in this full language? I don't think so. An E, I'll just make some of them up, okay? And so we want to know what is the string. We want to fill out this map. At the beginning, we know nothing. And so we can now go into to the left subtree and say, if you happen to find any encoding, then stick a 0 in front of it. Why a 0? Because we already have a 0 here. And then this tree will tell the same to its children. Like, it'll say to its second child, find me all those leaves and put a 0, 1 in front of it, because we have a 0 here and a 1 in. And this one will tell its left child, find me all your children and stick a 0, 1, 0 in front of it. And this one will say, hey, I found a K and I'm going to stick a 0, 1, 0 in front of it. The one over here will again go to this one here and stick a 0, 1, 1 in front of it. This one will do this with a 0, and it'll say, okay, fine, U was 0, 1, 1, 0. And so the table will get filled in as one recursively goes through all of the subtrees. And so that's the key step for encoding. Once you've built up the table, then you just need to look up the code values in the table. But filling up the table requires a recursion into the entire tree, and it uses, again, that prefix idea that you remember the prefix, kind of not asimilar with what you're doing in that homework with the printing. So that's what it says here. So in this fill encoding map, now we're giving this map that we need to fill in. We're getting our prefix. If we have a leaf, then we say, well, the prefix must have been the path to us. Otherwise, we ask the left to fill in its share of the map with a prefix that has a 0 stuck to it, and we tell the right part to do the same thing on the right. So that's how one builds up the map, and once you have the map, you can just look up the values in the map. So here is a final question about this. If you notice at what we did in this computation, we made a map from each character to a string, to the encoding sequence. And now contemplate a different way of building that map. I want to make a map that lets me quickly find not the character sequence, not the path, but the node. I just want to have the node. And so let's say I build this node, and then when I have that, what else do I need to do to be able to do encoding usefully? Let me set up the question, and then I'll keep talking. So here's my tree, and the map that I'm now contemplating to set up is I'm going to map, oh no, I don't have B and C. I'm going to map A to this node, I'm going to map L to this node, H to this node, and so on. So that way, I'm saving myself the work of finding these nodes in the tree. I remember in the map where each of them is. And the question is that useful for decoding, for encoding? And by itself, it probably is not useful, but what else would I need to do? So the first idea was, what if each of these nodes also had a pointer to the parent? You can build binary trees like that, and you're going to be seeing those in 146. It's often convenient for each node to know its parent, just like in real life. And so, you know, if the child node needs his laundry done or whatever, then so suppose we had those backlinks. Would we now be, and now suppose I have that I know that A is this node. How can I find out the encoding of A? So I have this node here, and now I go to my parent, and now I can check, am I the left or the right child? Because you can simply check, you know, is n equal parent.left or parent.right? And that way you know the last bit. And here you do the same thing. You can go up and check which the path of the parents is. Notice that these zeros and ones are not written anywhere, right? They're just indications of whether one goes to the left or to the right. So this would certainly work, and one would be able to recover the path. But it's just a little bit inefficient because it means that for every decoding step, you have to find your way to the root, which is a log n operation. But it would certainly be workable. And what was the other? Oh, let's see what people were doing in Piazza. So, some number of people said that would work, but not everyone liked it. So most of you liked the other alternative better, where in each of the node we store the encoding. Instead of having that separate map, we would store that in the node. That's perfectly fine. So you could perfectly do that, and it would certainly work. So in reality, both of them will work. So 3 would be the correct answer. So both of them would be viable strategies, but neither of them is dramatically simpler than just using the map. So that's why I used the map in the book. All right, so this is what this graduate student came up with, and now he is rewarded with having his name in every computer science textbook. So try to follow that, and I certainly haven't been able to. And so I think it's an interesting and beautiful algorithm, and it gives you the use of a priority queue. So I just wanted to for you to see it. And what to me is remarkable is how short the code is. That, you know, all of this code fits in, you know, under 10 lines of on each slide, and when you read through it, it's pretty much self-explanatory. It's actually much, much simpler than the code that you're going to be seeing on Monday when we're doing insertion and removal from a tree, where it gets kind of messy. So it's a beautiful algorithm, and, you know, that's something that's obviously useful. So I thought that, knowing that this wasn't going to fill the lecture, I wanted to talk for a few minutes about Lab 10. So it's not clear to me whether you perceived Lab 10 as useful or as a pain, but it is super useful material. Generally, you're going to be spending, most people in the future are going to be spending a fair amount of time at a terminal, and the simple reason for that is, so here I'm logging into a server from where I could mess with something like it's similar to the one where CodeCheck is run on. I have no idea where it sits. It could be on Mars for all I care. I mean, that's what it is like in the cloud. But here I can see, what I can see what stuff I have on there and so on. And everything that you do on the terminal. So knowing the terminal has become pretty much a survival skill these days. Whenever you need to deal with any server. And when you think about what kind of programming are you likely going to do, I mean, there's two kinds of devices that people program these days. They're the servers in the cloud, and then there are the little machines in our pockets. And believe it or not, you can have a terminal session into your phone and find out what ails the program in your phone that way as well. So the terminal is useful. And then the second thing that's useful once you've gotten better at working with the terminal is if you need to automate anything at all, that then being able to take a sequence of steps and write a little program that automates it can be a humongous time saver. And once you've learned like the basics of it, it really is a powerful technique. Like as an example, CodeCheck uses a somewhat funky setup for, CodeCheck is a little different from a lot of web applications. Most web applications, they will present a user interface that will connect to a database, and that's it. And they can be deployed to a server pretty simply by deploying the Java, Python, or whatever code it is to a server that says, I'm willing to execute code in that framework. CodeCheck, unfortunately, because it needs to be able to grade programs in C++ and Scheme and Java and all of that, then needs to be able to shell out to the operating system. And most managed server environments don't allow that. So when I deploy CodeCheck into the cloud, I need to deploy it onto a naked server that has nothing but Linux on it. And the way that makes on-demand computing work is that the cloud infrastructure notices that CodeCheck slows down to a crawl, and then it spins up more machines. So it actually, when you're there laboring at near midnight, the Google Compute Engine will spin up more machines to run more CodeCheck, but it is limited by my willingness to pay for it. And so that's why it's still not running as fast as it could. If I was willing to pay more money for it, it would be crazy fast even 5 minutes before midnight, because it could spin up more machines. Now when it spins up a new machine, what has to happen? It's a naked machine. It then needs to run a script that installs all of the components that make CodeCheck happen. It needs to fetch Java, it needs to fetch the application server, it needs to fetch the latest version of CodeCheck, it needs to install the C++ compiler, and whatever else one might want to have. And so there is a script that does all of those things in real time. When the machine gets born, that script gets executed and it installs itself so that it's, and then it launches the server and it's ready to serve. To execute the script takes maybe a minute. And so these machines, they get born, they get killed again when the load is low, and so it's essential that that script can automatically happen. So this automation is something that people need to do. The other kind of automation that you often need to do is that you just need to do stuff that that's really boring to do by hand. And I thought I'd show you something that you might run into. So here you can see what the grader gets when downloading your homework from Canvas. And so, soon some of you might be graders, and so you might be faced with this. Notice that Canvas makes a it doesn't like give you directories or some such thing. Even though the student here, and these are not the real ID numbers, fortunately, so I can post them without problems. So this student here has provided 3 files. Do they get put in a directory with the name of the student? No, they get put into these files with these crazy long names. Now, why is that? That's because Canvas is not just used by computer science classes, but in English classes. And the fear of the Canvas designer was that an English professor would be completely baffled by the concept of a directory. So they encode everything into files, hoping that that's not beyond the cognitive abilities of the English professor. So now if we wanted to make a directory that were to hold all of these here, then just imagine you have now 170 of these. So and you would now have to make by hand 170 directories. That would be unattractive, to say the least. But it's kind of difficult to grade otherwise, because if I now were to, what would happen if I just started unzipping these all?
You have a bunch of class files all in the same thing.
They would all be in the same place. I can try. Well, that didn't even work. I didn't even. Okay, I don't even want to. What would happen is exactly that, and I'm going to trash this because I just ruined it. So it simply wouldn't work. I would just have all of these files sitting on top of each other. So I must make these directories. But I don't want to make 160 directories by hand. And so this is where automation comes in. So if you know a little bit about the shell, then we can figure out, how could we extract these names? And so I'm going to show you how to do this. So first of all, notice that there's a loop. So I could say for f in star.zip. And I can just echo the file name, and now it echoes me all of the file names. But that's not what I want to do. I want to match the file name so that I can extract out this front piece. Now Bash has regular expressions, and so I can make myself a regex that just picks out this here. And notice that it's all a little bit tedious in that, do they all have late in front? No, they don't all have late in front. Do all names have 2 parts? No. As I know from looking at these names from the grader, there's some annoying students who have like 3 parts to the name, and there's one who has 4 parts to his name. And so so that doesn't really work. So what we have to do is we have to fish out everything up to this underscore. So we have a bunch of stuff that's not an underscore, followed by an underscore, and more stuff. So we put that into our regex. And now what I do is there's an operator for matching the regex, so I have to say if $x equals squiggle, $regex. For some reason in Bash you have to put a $sign in front of them. Then something phi done. So then what I'm going to do is I'm going to echo, and now what I'm going to echo is it is re match bracket 1. Oops. Why is it not echoing it? Because I didn't put tests in here. The trouble with Bash is that its syntax is different. Now is it not echoing it? I need to put 2 brackets. That's what happens when you do this in real time. Nope. Okay. Okay, now I'm going to cheat, as I did this earlier today. Oh, it's bash rematch, of course. Bash rematch. Okay, so now I must have gotten my match wrong because it matches only one letter. So let's look at our regex again. Ah, and that's because I didn't put a plus in here. And here they are. So now I have the name of just the students. So fine, I have them, but now I have them 3 times. I don't want them 3 times. So I'm running them through unique. Now I have them once. So for each of them, I want to make a directory. I don't know if I can use F twice. D. Notice now I have a directory for each student. And now I can go on, move those files into the directory and start unzipping them there. And I've done this with one line of admittedly incomprehensible bash, but I've developed it in a few minutes. Now I can start putting this in a script file, and the next time I need to do it, I don't even need to remember it. And so it is really, really useful to be able to experiment with this thing, to get closer. You've seen me making plenty of errors. That's what I always do when I do this. But eventually it comes out just so. I save it away in a file. And in fact, I have a file like that. That I call Canvas Unpack. And here is Canvas Unpack, and it has a bunch of gobbledygook that does something similar. So I've developed it once, and then I never had to worry about it again. And next time that I get one of these zip files that contains other zips inside, I run my script, and it doesn't bother me. Given that as a grader, you have to do this, 26 times a semester, the hour or 2 that it took to fiddle this stuff together, repays itself pretty quickly. So it is a really, really useful skill, and people use it for all sorts of things, for finding things in log files, for backing up projects, and for automating all sorts of aspects of life. And so every programmer has some of these scripts that solve some pain point for them. And so I really want to encourage you to spend a little bit of time on getting better in Bash, and or whatever shell you choose. The reason people choose Bash is not that Bash is wonderful. In fact, it's quite awful when you look at the programming language with its crazy constructs, but it's everywhere, except on Windows. But these days, that's no longer so important. So for the final, for that reason, I'm going to ask some simple Bash question. I mean, nothing like what I've just shown you. That's too complicated. Or if I want to go that far out, I would give you the bits and pieces and have you put them together. I might tell you, this is how you do regex matching in Bash. Now do that with a bunch of files. But so go through this lab again before the final, so that you know how to do the basic constructs and play with it a little bit. Just open up the console in the virtual machine, and if you use Mac in your regular machine, and mess with it a little bit, so that you get a feel for how does command line completion work, how you can do this kind of experimenting that I just did, where I just try 10 things until something works, because that would come in super handy in the final. So there will be one question like that. Any questions about this? All right, so that's what I have for today. Then have a good Thanksgiving.